time. We were discussing about stability of an LTI system, and why stability is important, because we are transforming a signal. And how are we doing that? Ji. Ji. जी जी add the indices together. मसलन क्यों कब नहीं करेगा? It will work.
सर रेफरेंस को एक सेट करना पड़ेगा, मतलब 100 पे आपने कन्वोल्यूशन में तो आप एक रेफरेंस से करते हो
जी जी,
तो 100 से स्टार्ट होगा, ऑनवर्ड जाएगा, या -40 से आप उसको
let me just reiterate what I said. I said if a signal starts at N1, goes to N2, and another signal start at N3 to N4, then the output will always start from N1 plus N3 and will go to N2 plus N4. ठीक है? Always, it is always like this, because it's a linear and time invariant system. And what is time invariance? That if you vary a signal in time, ठीक है, it is not going to affect the output. So all we are saying, let's assume this is 0 and this is also at 0. So perform the convolution, okay, and then move the output. Okay, so the output, the actual place of the output is here, because this is where you are going to see the first overlap. Okay, so this is where you are going to see the first overlap, and we can do this after the class if you want me to, just spend some more time with you on this, but this works. So the stability is important, because we are transforming a signal and we want to make sure that whatever we have designed is in h of n, it convolves with a signal x of n. So it takes every sample of x of n, uses many samples of x of n, or the previous samples of y of n, and computes a current output sample. And we want to make sure that if we input legal samples here, legal sample means they are bounded input, bounded output. Okay, so bounded input means they are bounded by some value, by some largest value. You say a sample will never be an illegal sample, it will always be a value less than whatever is the maximum you assume that the sample will take, and then you want your output to remain in that limit. So all the output samples. So for the criteria is that for a system to be bounded input, bounded output stable, bounded means finite, which is less than infinity. Bounded mean a value which is less than, which is not infinity. Okay. So this is the criteria for stability. We'll come back and hit this criteria. Then there are a few more definitions which are important. One is causality, and causality means a system is causal if it only requires the current and the previous input values. Right? A causal system is important, that you have designed a system which does not require any future input sample to compute the current output sample in time. So n, remember, is the index in time. So to compute an output at n, the index where you stand, you only require the current input and the previous input, no matter how many, but no future input is required to compute a current output sample. If this is so, a system is called a causal system. Right? This is important at least in 1D. In 1D transform, or in the 1D signal, where you are continuously acquiring a signal and at the same time you are computing the output sample. In image processing though, you can have future values, because these are pixels, not time. So you acquire an image, and if you are processing an image, so you are on this pixel, if you are computing something, so you use the pixels here, pixels here, pixels here. So you can use any of these pixels because you have the complete image. Similarly, if you have a pre-acquired signal, you have all the future samples. Okay, so there you can say that because I have a pre-stored signal, you are operating, let's say, on a song. So you're just transforming a song, then you have the entire signal. So there the causality is not important, but otherwise if it is real-time signal processing, 1D signal processing, causality is important, and it says that you only require current and the previous input values to compute an output sample.
How a causal system will start?
G?
How a
Causal system is, remember, it's not about the input. The causal system, causality means that the output, to compute an output at y of 0, you only require an input at x of 0 and the previous input values. Okay? So it will start, let's say if you have whatever convolution equation, remember, you flip, and the very first time you get an overlap, you are only using one sample of the input and one sample of the impulse response. So this is your first sample, this is how it starts. Then you move, you are using 2 samples, then 3 samples, then 4, 5, 6, and ultimately you are using L samples. Let's say L is the impulse response. So this is to compute the if you remember the convolution summation, it says that it is h of 0 x of n plus h of 1 x of, and it goes like this. So this is a causal, this formula represents a causal LTI system, because to compute a sample at y of n, I am using the current and the previous input samples. If in this formula I put xn plus 1, this is a non-causal system. Why? Because at n I require future value. So it can always start. Again, it will start because just you will be using only one input sample, then 2, then 3, then 4, and then you have full overlap, and then you just keep getting full overlap. So this is and the proof is simple, that how do you judge that whether a system is stable or not? Okay, and it comes out to be a very simple check. All you have to check is that your impulse response should start from 0. Okay, it should not have any value. Your impulse response should not have any value at negative indices of n. That's a simple check. Okay, if I say, is this a causal system? -1, if this is the impulse response. Answer is no, this is not a causal system, because h of -1 is non-zero. This is a non-causal system. Okay, because why? Because once you flip, and remember I already told you that the start, let's say input start at 0. If input start at 0, okay, but your output is going to start at what value? -1. Even before the input starts, you need an output value. See, and if you write an equation for this, the equation will be, because remember this, it says n goes from, or the k goes from -infinity to infinity. H of, this is the convolution summation. Okay, let's say for this system, if you open this up, so k is, the h of n is varying from -1 to 1, otherwise it is 0. Okay, so the summation is varying from -1 to 1. If you open this up, you get h of -1, x of n plus 1. So this minus will cause a future value in the expression, which you don't like. Okay, so it means you must not have any h for negative indices. Positive indices is fine, even the 0 is fine, because once you write h of 0, it is x of n, and once you say h of 1, it is x of, so this is okay and this is not okay. So means that the summation must not start has any negative, it should start from 0 to infinity. Then you are fine, then the system will be causal. So this is the definition of causality, that your h of n must be 0 for negative indices of n. So whatever system you design, you will see that it has some consequences, and we will keep fighting with the consequences, but to be a system to be causal, h of n must be 0 for negative indices of n. This is important. Okay, and this is the proof that it must only run from 0 to infinity, and for all negative indices -infinity to -1, this expression must be 0, and this expression can only be 0 if n is 0 for negative indices of n. Okay, so we have seen this, that once you open the summation, all the negative values of k will contribute future samples. -1 will ask you to have the next sample, and +1. -2 will ask you to have next to next sample, the future. So all the negative values in negative k's means here. A negative k here means that it is in the negative time domain, or negative indices. So we covered this. This is a good example. If I say this is a linear and time invariant system, h of n, a of n, u of n. And let me just keep reminding you, the system means that you will be convolving this system with a signal to get some desirable output. Okay, it's not in air that it's just, though it's a mathematical expression, but it's a very real system. We use it a lot. This system is used a lot in signal processing, and this system says that it's a is a constant, n is the index, un means that it is only for 0 positive values of n. So because un starts from 1 and then it goes on and on, so it is only for positive indices of n, for negative indices it is 0. So this is a very real system. It is used a lot in signal processing, and this is the simplest system which you can use in signal processing. Though it seems it has an infinite impulse response, but this is the simplest, the cheapest system which you can use, and it says its impulse response is this. And we, in the convolution problem which I did here, I used this a of n, u of n. I showed you that this is how you convolve and all that. So it's a very real system, and its first sample is a because it is a of n, u of n, and a usually is a value which is less than 1. Okay? So let's say it is 0.9. So this is how it will change: 0.9, 0.9 square, 0.9 cube. So it will keep. It's an exponentially decay. This is an impulse response. This is something which you design, and how you get 0.9, it is a design problem. Is it 0.9 or 0.8 or 0.6? It's a design problem. It has a consequence because that is the only, this is the only design parameter you have in this problem. Okay? If you are asked to design a system with a and u of an impulse response, the only thing you need to design is what? A. A could be positive value, negative value, but should be, its magnitude must be less than 1. We'll see why, because otherwise it will become unstable. If you make a greater than that, it will not obey the stable, yeah, because what that says that add all the samples together. H of n, add all the samples together, find out if you get a finite value. Even if it is 1, what if it is 1? So you have 1, 1, 1, 1, add 1, 1, 1, 1 infinite time. What do you get? Infinity. So it means even this is not a stable system. 1, 1, 1, 1, 1.
If it is less than 1 and it is a continuous signal है, infinity तक जा रहा है, तो फिर भी इसका sum less than.
Oh yes, this is, you know, go back to the FSC books. You'll find this is a geometric progression. If you have a progression like this, its sum is always 1 over 1 minus a. Use a calculator. Okay, just start saying 1, 0.9 plus 0.9 square plus 0. Just keep doing that. You will find that answer will be 1 over 1 minus a, which is 1 minus 0.9, which is 1 over 0.1, which is 10. So you keep adding it, the answer will be 10. So this is a finite number. Okay, so keep adding, use calculator. It's a good exercise. Just keep adding. You'll find that slowly, in fact very quickly, it'll move to 10 and not move from there. So it means that if you add all these samples together, you're not going to get anything which is greater than 10. Okay? If you plot it in MATLAB, it will say it'll grow and then it'll go do like this, and it'll never hit 10. Okay, in perceivable value of n, it will never hit 10. It'll get very close to 10. Okay, so this is the reason it is a stable system by definition of LTI system, because the summation is a finite number. It's a stable system. Stability is important, but I just want to highlight that once we are saying h, a, and u of n, it is not out of the world. It is something which is very real, and we use it a lot. And if it is negative, interesting is what if it is minus 0.9 n u of n. How does it look?
Positive 1.
So it is positive then negative, then positive, then negative. This is also very real system. Okay, it'll just a positive and a negative, positive, negative, positive, negative. This is how it will behave. Like this, h of n will be positive, negative, positive. It has its own consequence. So this a is magical number, and you cannot just come up with a number. They are design tools. You need to know what you want to do, and then you define a. But the important thing is, in this, the only design parameter is a, and this is a which is going to affect your system. If you choose a1, it is going to be unstable system. If a is greater than 1, again an unstable system. A less than 1 will be a system. A negative will be another system. It will be stable, but quite opposite to a, which is a positive value. So we'll try to have a MATLAB exercise where you experiment with these things, like a, keep a positive, keep a negative, then see how it behaves, what it does to your signal, right? So it is stable because this is the magnitude square, which is 1 over 1 minus a magnitude, and it is going to give you a finite value for magnitude a less than 1. Is going to give you infinite value if it is 1 or greater than 1. Then once we talk about systems, though convolution is one way of implementing or representing a system, but another way to represent a system is through difference equation, and this is very close to what you see in continuous or analog system, which are represented by differential equations. So if you put a system or a circuit together, the relationship of that circuit, if you put a capacitor and a resistor, remember you must have done this in your circuit analysis course. This is a system which is going to transform your input. You put some input, the output will be changed depending upon the value of resistor and capacitor, and here the design parameters are the value of capacitor and value of resistor. So digital signal processing can effectively replace all the analog circuits, okay, and that is the promise of signal processing, that it can replace all the analog circuits, and you can replace an analog circuit by a formula. That whatever the circuit is doing, you can precisely come up with a formula which will do the same to your signal. So you take a circuit, a board, and you throw it away and put a processor, digitize your input, and you will get a digital output, then change the output to analog signal. So this signal processing will help you to remove analog circuits, right? And we'll come to the point that what can be replaced, what cannot be replaced. But at this point, theoretically, you can almost remove any kind of analog circuits with a program, a computer program. What you learn in this course, you can use that learning to replace an analog system. So this circuit and all the circuits are represented by differential equation, but because this is a discrete time system, so its equivalent in signal processing is a difference equation. Okay, it's easy to perceive. A difference equation is basically an equation which uses previous current and previous values of x and current and the previous values of y to compute the current output value. So this is a better to implement or realizable expression which says, to compute an output sample, you use k runs from 1 to n. So k runs from 1 to n, or this is y of n minus k, and these are constants. So this says that to generate a current output sample, one way is that you use convolution summation. Convolution summation sometimes is non-realized, it's not realizable. Why? Because if your impulse response runs from 0 to infinity, for example this case, h of k x of n minus k. A very simple system where your h of k is, h of n is a of n. So h of k will be a of k, and it runs from 0 to infinity. So to compute every output sample, you need to do how many multiplications? Infinite many multiplications. You compute just one output sample. If you use convolution summation, it requires you to have infinite number of multiplications just to get an output sample. Okay, obviously this is not desirable. So though the convolution summation is not desirable, not realizable, if h of n is a signal which runs from 0 to infinity, we call this an infinite impulse response system. If your system is an infinite impulse response system, this summation cannot be used. In theory you can use it, you can use the expression convolve it as I did in my example last time. So you can use it theoretically doing it on a paper, but to actually implement it in software, this is not useful. So for systems which are IIR system, interestingly, this can be, this whole complex expression can be replaced by something which uses previous values of output and the previous values of input to give you an infinite impulse response system. So again, it's important to understand infinite impulse response systems are very effective systems. Right? They are very effective because with one parameter or two parameters you can control the entire system. So very effective, very useful, very cost effective, because only you have to design one parameter, two parameters, so let's say three parameters, but just using those three parameters, means three numbers, you can design a system. On the other hand, in finite impulse response, where h of k is finite, usually you need to have a much longer impulse response, maybe 200 samples, maybe 100 samples, maybe 50 samples. So design problem is more complex. If h of n is a finite signal, design problem is more complex to come up with those numbers because there are more numbers. Whereas in case of an IIR filter, I already showed you an example where there is only one design parameter. So you can even guess. So there is only finite number of guesses. You say okay, 0.2, 0.3, 0.4, at least you can do hit and try, you can come up with numbers, but as the number grows, obviously the design will become complex. So the important point is that a convolution summation is equivalent to a difference equation, and we'll shortly see how a difference equation uses the previous values of output as well as the input. Okay? But the convolution, as you can see here, it is not using any value, any previous value of the output. It is only using previous input values. Let me give you a good example, a very simple example, which says, let's say I ask you to add all the samples wherever you are, wherever the index n is, I ask you to add. This is a system where my requirement is wherever you are, add all the previous samples. Okay? So let's say you are at index 100,000. I ask you, okay, you are at 100,000, add all the values. Okay, it's definitely going to take you forever to implement such a system, because wherever you are, you just go and add all the values. Then you get next input sample, again you do this, you get next input sample, again you do this. It's obviously it's not a realizable system. After some time it's going to die. The system is going to die because you will be getting more inputs than the time you have to add all the input samples. But a common sense will reveal that why am I really adding all the samples once I already have a summation of all samples once I did this. Once I computed this, I have a sum of all the samples here. So I should just add this sample into the previous output sample to get the same effect. Obviously, because I already have accumulation of all the samples. The answer is with me. Once I am computing y of n, in y of n minus 1, I have the effect, the cumulative effect of all the samples till n minus 1. So I should only do this. This is a difference equation. Okay? It is implementing a very complex system, which says wherever you are, add all the samples together. Okay? So this is a very complex system, so to say, because it requires so many computation, but look how simple it is to implement. Previous sample, add the next current sample. Previous output, add the current output. So it will basically help you to implement a system. A difference equation is important because it helps you to realize a non-realizable system. And this and its impulse response is, we'll come to this, but its impulse response is u of n, which is not a stable system. Once I say this system where you are adding all the values, in fact it is this system whose impulse response is all ones. And why? Because if you convolve, okay, if you flip this, remember if you flip a u of n and this is your input sample, so wherever you are at n, what are you doing? 1 multiplied by something is something, the same thing, and you just add. Then you move it and then again, so you have to add So wherever you are moving this u of minus k plus n or whatever, basically you are adding all the samples. So but we'll come back to this point, but here the important point is that you can realize an infinite impulse response system by a difference equation, and usually these systems are more effective systems, more cost effective system at least. But the problem with these systems are that they may be unstable. If you are not careful, these systems may be unstable system, and here just it is one design parameter. If you don't choose it correctly, it's going to affect the entire system. In FIR system there are 500 values. If you are not correct about one value, it will not hurt you badly, but here this just one value will hurt you badly if you don't choose it correctly. So this is the reason. So here is another system which says y of n is equal to a y of n minus 1 plus x of n. Okay, so it's system, you say take the previous output value, multiply it with the constant, add the current input value. Okay, so let's try to figure out its impulse response. So we say this is a system so this is a input output relationship, it's a difference equation. What is an impulse response? Once x of n is what? Impulse response is once your input is an impulse, right? So if your input is an impulse, then output is called an impulse. So it's simple definition that input is an impulse, output is impulse response, right? So no matter what type of system you have, impulse response simply means put an impulse, get the output, and that is your impulse response. What is an impulse? Impulse is a signal which is 1 at 0, otherwise it is 0. Let's say the system starts at 0. So y of 0 is a y of minus 1 plus x of 0. What is x of 0? X of 0 is 1. Okay, and why we are saying this starts from reset. So y of minus, there is no previous output value, you are just starting a system. So y of 0 is equal to 1. What is y of 1? So again put this in this equation, it says y a of y 0 plus x of 1. What is x of 1? X of 1 is 0 because there is no input, you just give an input. What is y of 0? 1. So you get y of 1 is a. Similarly you get y of 2 a square, y of 3 a q. So if you give an impulse to a system like this, this is what you are going to get at the output, which is the impulse response. H of n is equal to a of n u of n. You see, so basically this impulse response is implemented by an equation like this: 0, 1, 2, 3, 4, 5, keep going like this. First sample is 1, then a square, then a cube, a4, and just keep going like this. So there are good things about an IR system, the bad things. The bad things are, even if you turn off your input, you keep getting outputs. The output never ends because it uses previous output value, you just keep getting. Okay, if you don't turn off your system, okay, if you don't turn off your system, you only turn off your input, though it will die down. If it is a stable system, you give an input, you take that input away, you keep getting output. Theoretically you keep getting output till infinity, always you get an output. Practically, if it is a stable system, the output will die down. If it is an unstable system, output will go up. Right? This is the case. If it is a stable system, output will die down. If it is an unstable system, it will grow. The output will grow. Every time it will grow, and you can check it. If a is greater than 1, so you get 1, then you get a. Let's say a is 2. So first time you get 1, then you get 2, then you get 4, then you get 8, then you get 16. So every time you are getting a bigger value. So it'll basically be unstable, and this is what it will do to you. But important point here is that a difference equation is very handy in implementing systems, and a very easy software program. If you are asked to write a program which implements this system, all you have to do is every time you get an input, you only have to save the output sample, the previous output sample, multiply it with A, add the current input, get the output. Next time again you get the input sample, so you repeat this. So very simple to implement such a system in software, right?
Sir, A को gain कह सकते हैं?
A not really. Gain होता है कि if you have an input and you say I'll multiply input by A, so this is gain. This is the definition of gain, that you are only either you are amplifying your input or you are attenuating. This is not really gain, this is indeed a LTI system which is going to affect the output of your system. So this is the same example. Initially reset condition, the difference equation has impulse response which will die down like this. Okay, so this is good. Now in the second part of the course we'll keep coming back. This is a very interesting and nice expression. Why? Because now look at the same thing from modeling perspective. Now I have a way to just define an A. Okay, this is good. I have a way to just define an A and an impulse, and I can generate an infinite signal, right? So this difference equation tells me that I have a way in signal processing that all I need to do is define an A, give an impulse. So how many things are there? Just A, and I can generate an infinite long signal. We do the reverse in modeling. I have a signal which may be infinite or may not be infinite, but a very long signal. Let's say it has 1023 samples, 1024 samples. I don't want to transmit 1024 samples. I somehow know that these samples are coming from a system. Every signal comes from a system. Even once I am talking, my voice is coming from a system. If I have this magical way of figuring out the system through which the sound is being produced, so all I have to do is that instead of transmitting this, I only need to figure out A if it is just one, or there may be few more. So let's say I say there may be, let's say in my difference equation there are 9 of these. Okay? So in the reverse problem, in modeling problem, you are given an output, you figure out a system which can generate an input. Usually it is an impulse. It may not be an impulse, it may be 2 impulses or maybe 3 impulses. Usually in voice it is 2 or 3 impulses. It is which is equal to pitch of your sound. So it is the impulse which goes through the system, the natural system, and a voice is produced. So this is an interesting problem because it enables you, FIR will not, it enables you from few parameters generate a very long signal. So this is what in compression this is what is done. In modeling this is also done, that you take this signal, you spend time in figuring out a system, you drop this, you send this and this. Okay, the receiver will take this and simply implement a difference equation, put an input and generate all the samples at the output, and those samples will for sure will be very similar to these, because you spend a lot of time at the transmitter, because you have the original signal, you have the system. This is called a synthesis by analysis method, because you know what you need to produce. Okay, so you just come up with anything possible, keep generating, keep checking, am I close, am I close. Once you are really close, you say, okay, I think I'm very close to what it needs to be, you send that. Okay. But this is again very important to understand. We'll spend more time on this. जी
सर आपने बात की कि ये जो किसी सिग्नल दिखाया था कि this is used a lot in
signal processing.
But on the face of it, if we have the output like this, I mean ये तो बड़ी कोई restricted किस्म की application नहीं होगी.
No, this is the impulse response, not the output. देखिए, input will not be an impulse. Input is your voice. Input is something which is coming from a sensor. ठीक है? What I showed you is output of an impulse. but in real life you will have a real signal, voice hai, kuch hai, okay. So in real life you will have a signal, because you're feeding this a signal, and that signal will be transformed, not an impulse. So this is the impulse response, and impulse response is only generated once you input an impulse. But if you put in a real signal, it has some desirable characteristics. This system, it's a low pass system, we say it's a low pass system. If you have high pass noise, okay, and you don't want, it's very high sampling rate and you don't want to spend too much on this, this is the way. You just put A and pass your signal through this filter. And once we come to frequency domain, we will analyze the system. That's why the second part is. So here we are just learning that, okay, this is a system. Then second part we'll say, okay, how to analyze a system. What a system is capable of doing. The second part. The third part is design.
पिछली वाली एग्जांपल में जैसे आपने बात की कि ट्रांसमीटर और रिसीवर वाली साइड.
जी जी.
So रिसीवर वाली साइड पे जब impulse response पहुंच गया, so then the actual signal जो input samples हैं, they will go through the impulse response to generate. Well,
precisely. The actual signal will go through the impulse response, and what you are designing, okay, will go through that, and then you get an output. See, again, once we do MATLAB exercise, I would try to design exercises around a real system, like playing with voice or playing with images, so that you can actually see what is happening. Okay, so this is the difference equation. This is what we have already seen. Don't worry about this. This is the same example, but it's just assuming a previous condition and not an impulse, but an impulse multiplied by k. It's a slightly different interpretation, but this is if it is initially at rest, and this is more than enough if you understand it. So for a difference equation, we say there are two types of system. One system is where you are not using any. This is same as the convolution. If you look at the difference equation, if you are only using the current and the previous values of the input, and you are not using any previous output sample. Here you are not using any previous output sample. If this is the case, it is usually called a moving average system. Okay, a moving average system is a system where you are not using any previous output sample. You are only using finite number of input samples, and this system is called a moving average system. Okay. So this is all you do, and here the BKs are the design parameters. You need to figure out all BKs or H. This becomes, if you write this B as H, it becomes the convolution equation. Okay. So the difference equation with no previous output playing any role is a convolution equation. A difference equation with no previous output playing any part in the equation is basically a convolution equation. But if the previous outputs are there, then it is not a convolution equation. So it will always be bounded input, bounded output stable. So means a finite system, usually we call this a finite impulse response system, is usually stable, and you need not to worry about the stability of an FIR system. Right? It is only the IIR system where you need to, or we call this an autoregressive system, okay, can be unstable or may be unstable. Here the A parameter is going to govern the stability of a system, and this may or may not be stable system. It is, we know it is unstable if A is greater than 1. So this is the difference equation, and A is going to define the stability. So for a finite impulse response system, the reason, okay, there are 2-3 reasons, we'll keep coming to those reasons, but a good reason for using an FIR system is that you need not to worry about stability. FIR systems are always stable. And a good reason to use an IIR system is that they are effective. Few parameters are controlling the entire system. They are cost effective, okay, but their stability is an issue. So people usually where the stability is an issue, or the value of A is an issue, they try not to use it. Okay. But another important point is that for a system, it's your choice, it's a designer choice whether to use an FIR or an IIR system. Both are doing the same thing. They are transforming your signal. So in MATLAB, you must have already known that this is the convolution function which is used to convolve, and a filter function is used for a difference equation. a filter b comma a comma x will filter out your signal. So filter y is equal to filter b comma a comma x. X is your input, and so you pass your, it is effectively equivalent to passing an x through a difference equation with b's and a's coefficients and getting an output sample. So this is a filter command in MATLAB where you design b's and a's, and x is your input signal. You pass it through a filter and get an output y. Usually even in MATLAB, because remember that you are implementing a system which just keeps running. So you turn on a system, whether it is a communication receiver or a control signal or a control system, it just keeps running. So usually once we are designing MATLAB simulation for these systems, we don't say that you have only this much input. Input is always coming. So what you do is you just buffer your input. So usually you use two buffers. This is an implementation, from implementation perspective. Whenever I am realizing a signal processing system, I always assume I have two arrays. I am filling one and processing the other one. So you have a ping pong buffers. So I'm getting input, I'm filling this. Okay, I'm processing this. Once I fill this up, I process it and I start filling this one. And I need to be fast enough that before this gets filled, I must have done with processing this one. If I am not, then it means that I will lose samples. Okay, because it's a real-time signal. I'm continuously getting samples based on the sampling rate, and I'm just filling a buffer. I process it and I'm filling because I cannot stop my input. Input is continuously coming. Let's say if I'm just processing an FM radio signal. Okay, I want to design an FM radio in software. I put an antenna and I say I'll demodulate this FM radio in software using MATLAB code. So I'm continuously getting a signal. From the antenna it is coming, and I have a routine where I'm just collecting samples, bringing it in my MATLAB. So I fill this buffer, and now I have a system which is demodulating this FM signal. Okay, and at that time, once I am demodulating it, the samples are keep coming. So I use another buffer to fill those samples, and I process these samples. So process this, and I need to make sure that I am done with processing this before this gets filled. If not, then I lose samples. Obviously, if I'm still processing it and I've already filled it, then I lose samples. So this is where you need to be fast enough, and this is the cost of the system. Once I keep coming back, the cost of a system is how complex your algorithms are. Can you do your algorithms before you fill another buffer? A very simple check. It's a very simple check we use always, that usually a routine which is filling this buffer, and you need to done with this and come here and wait. If you're not waiting, if you're done with this and this has already done, it means you are late. So you need to go change your algorithm. And what do you do in changing your algorithms? You need to reduce the complexity of your system. You say, oh, I'm doing too many multiplications, too many additions, I need to reduce it. So you reduce the complexity. So it is always a trade-off, that you design something very complex, very easy to design. And once we get to the design, find out. And you say, no, this is taking too much time. You come back, you reduce the complexity, because it will not be real time. And till the time you are in real time, you are fine. The complexity is fine. If you're not in real time, then it means you cannot go back and change your system, because system is hardware. It's difficult to change a physical hardware system. If it is a Pentium processor, you cannot throw it away. You say, I think Pentium 5 is not good enough. So you can say that, but usually once you are designing a system, you are over with designing a system, and now you are implementing. The design phase is over. So that's why design phase is important, because you need to design fast enough system which can keep up with the number of samples you are getting. So why I want to highlight this, that usually the filter command we use is this one, which says you process a buffer. You use b comma a comma x, zi and zf are the initial and final conditions. Okay, these are the initial and final conditions. You cannot just take a buffer, and reason is, let me write a difference equation. It says y of n is a naught y of n minus 1 plus a1 y of, इसको मैं a1, let me call this a1, a2 y of n minus 2 plus b naught x of n plus b1 x of n minus 1. Okay, now remember these are just numbers. How do you get these numbers? At this point you don't know. A1, A2, B0, B1, these are the numbers. So once you get to the design, we'll find out how you get these numbers. Let me just, out of my head, I write numbers. 0.3 y of n minus 1 plus 0.6 y of n minus 2 plus 0.8 x of n minus 2 x of n minus 1. Okay? So once you design a system, these will be constant values. So once you start implementing this system, you get a buffer, let's say 10 samples. Your current sample, your previous output, let's say it is 0, you start with the current sample, you get a value, then you get another value, get another value, get another value. So you consume all 10 samples. Last, once you are computing y10, what do you need? You need y of 9, then you need y of 9 and y of 8, and you need x of 10 minus 2x of 9. So this is the last time you have the 10th sample. Okay, now the second buffer has the 11th sample. So you say, okay, now I need to compute y of 11. You need to have y of 10, and you need to have y of 9. You also need to have x of 11, which is the current sample, but you need to have x of 10 as well. So to keep all these states, MATLAB uses the Zi and Zf concept. Okay? So you need not to worry about keeping this and throwing this away. MATLAB will save these values for you. So you only need to remember that once you are using MATLAB to process a buffer, then another buffer, then another buffer, which you use this function b, a, x, zi. Zf will save your condition. Next time once you come to process the next buffer, this zf will become zi. So this will save the states for you, which is y of 9, y of 10, x of 9, x. So it will save the states for you. So come process next buffer, you take these values. So you are saying MATLAB, take the values which I saved once I was processing this buffer. So MATLAB will use those values. Okay, and then you are only providing MATLAB with the next buffer without worrying about saving yourself the previous values which will be used for the next buffer. So this function is very handy, Zi and Zf, because at least once we are designing a system, I always ask my designers to design what can actually be ported in C program or in Verilog. Don't just assume that there is a huge big input array and you process it and you get an output. No, assume that you are getting samples on buffer by buffer basis. You design your MATLAB code that you get a buffer, you process it, then you have another buffer. So write MATLAB code like this so that once a person who is actually coding it in C can understand. Otherwise it will be very hard for a person who is coding your algorithm in C to understand what you are doing, because he is not getting all the sample, okay, at once and it just goes through the system, because it's a real-time system. You get samples, you process, you get samples, you process. So this is very handy for
the system depends upon two input samples, as the example you gave now. And the stage will come when one sample will be in one buffer and the other will be in a...
That's what I'm saying, that usually this will keep the states.
That first buffer will be clear at that stage.
But the MATLAB has saved it for you.
Last value.
MATLAB has saved those values for you. See na? So to summarize, we have covered the convolution summation, we have covered the causality, we have covered the stability, we have covered the trade-off between an FIR and an IER system. Okay, and so we also covered that FIR systems are always stable. We have also covered the cascade and the parallel form. Okay, so we have covered the LTI system, at least the time domain analysis, the time domain perspective of an LTI system. Now let's now come to understand that why do we use a system? Why are we using a signal processing system? Okay. So usually once we use a system, there are two ways to design a system. So in the first part of the course, we are covering a system which you predesign. Before you actually go and implement it, you use MATLAB, come up with a design. What is design? Design are just those numbers. Okay. So a predefined, not an adaptive. A system can also be adaptive. We'll come up and usually we use this notation to say that this is an adaptive system. You need to design it in real time. Okay. All those parameters which you write, for example, I wrote this y of n a1 y of n minus 1 plus a2 y of n minus 2. This is a second order system, b0 x of n. So this is a big science to figure out the complexity. This is the complexity that I require two outputs and previous output sample. This is a complexity of, it's a second order system. Let's say I know I am going to use a second order system. Okay, so I'm done. Now if I pre-design these numbers and these numbers don't change throughout the life of the system. You design it in MATLAB, then you take it on your actual system. So this is a static system, it's not going to change. On the other hand, on the fly, if you are designing this, every time you process a buffer, you first design these numbers. That is an adaptive system. So you need to design it on the fly. So there are two parts to that system. First you design, then you implement. Once you design, there is a very complex way of designing, coming up with these numbers. That is not a simple science. People use neural networks, people use all kind of stuff to come up with these numbers. Once you are in real life doing it, okay? In real life, why you do this in real life? Because your system is changing all the time. A good example is an equalizer, mobile phone equalizer, which is you have a mobile phone, you are continuously moving, you are in this room, then you are outside the room. Okay? Now it needs to continuously figure out where you are. What type of system is the signal going through? It needs to come out with that, and only then it can cater to cancel out that system. So this is an example, a good example of an adaptive system where you design and so in real time you design and you implement and redesign and redesign. All the time you are redesigning. And you can check if it is slowly changing or fast changing. If you're moving very fast, it is changing very fast. If you're just sitting in your room all the time, it is not changing very fast. So the parameters will not be changing very fast. Okay, so you can figure out that, okay, I think it is not really changing. It's a slowly changing system or it's a very fastly changing system. So you figure out that. So these systems are usually designed to cater for dynamically changing nature of a system. Okay? A dynamic and adaptive system. The static systems are usually designed where you already know. This is what I want to do. And when do you actually know? Usually those are the frequency selective filter. This is something you know. Frequency selective filter. So these are usually something which you know for sure. You say, okay, I know these are the frequencies I want to keep and these are the frequencies which I don't want to keep. Again, example is the FM radio example which I gave you. Let's say I ask you to design an FM radio in software. So you acquire, once you acquire, you have all the channels coming into your system. So you through an analog front end, you capture a spectrum. So 99.9 FM, 100 FM, you know. So all these samples get into your system. And I want you to only give me the 99.9 FM. You say, okay, this is an easy problem because it is a defined problem. All you need to do is say, I know I only need to put a filter, select this, and remove all the other frequencies from the signal. This is a predefined system. Right? And usually if I say, okay, I may ask you 99.9, then I say 100, then I say this. So there are ways. You say, I think I should bring whatever the desired channel is, I should bring it to 0 If it is 99.9, I bring 99.9. I bring 0 here. If it is, I bring 0 here. Okay, so that's what you are doing once you are moving the knob of your radio, that you are bringing that to 0, and then you pass. The system is same. You bring it to 0, now you have one problem to solve. Otherwise, you have 10 problems to solve. If I ask you 99.9, you need to do this. If I ask you 100, you do this. If I ask you, no, not one channel in software, give me 10 channels. Let's say I'm making a soft radio. I want you to put it in a computer so anyone sitting on a LAN can just pick a channel and listen to that. It means I ask you to give me all the FM channels. For that you say, I will take out this, I'll take out this, I'll take out this, I'll take out this. So then you have to put how many systems? 1, 2, 3, 10. If there are 10 channels, you put 10 systems. So 10 frequency selective filters. So for every filter, the coefficients will be different. B0s, and you have basically, for some reason you say, I will only use a second order IAR filter to select a channel. It may be good, it may not be good. We'll find out that. जी, it is not trivial. देखिए होता ये है, the trade-off is, if you choose, let's say only 2 coefficients, its cutoff may not be that good. तो क्या करेगा? It will bring part of the signal from other channel into your signal. You say, no, I really don't like it because I am now not really listening to one channel. There is a residual of 2 channels coming. So you are listening to music and then the news and the other part is also coming. You say, no, there is something wrong. You start increasing the complexity, the order, and what order will usually do, will do all these experiments. It will start making it sharper.
Variable taps or tap and order both?
It may be tap and order both. It depends. Sometimes you say, I will fix the tab. I don't want to really, so then you have to solve 2 problems. Usually you say tabs are fixed, but sometimes tabs are not fixed. Okay, you say tabs is one variable and the other variable is the order, the values. But here it is, you are sitting in MATLAB, capture this whole spectrum, then do a lot of experimentation to come up with the optimized, which you believe is now this is the optimized system, that you have 10 frequency selective filters and you are passing your signal through them. Each one is giving you your desired channel. Okay? So this is where you are processing.
Changing the order will change the entire philosophy of the program, buffer size, and everything.
Precisely. So that's if you increase the order, you pay more money, you get better things, but sometimes how better can you get? It depends upon the power of your system. You say, oh, now I start losing samples. You start losing samples, you are out of the game. So you again come back, you say, no, I need to come up with a system which is more cost effective. So it's a very difficult really game, because once at a system design, once you are designing, you really don't know the complexity. You are only asked, we have designed so many systems. Once you are designing, sometimes you throw more power in a system in anticipation. For example, we designed a receiver where we place a digital signal processor. We said we may be using it, there's FPGA, digital signal processor microcontroller. We never used the DSP because we could able to handle that, but just in anticipation that what if not, So sometimes you throw, because if not, then you are out, because a system design may take you a year and a half, just designing boards, bringing up that board, and if that system is not powerful enough to meet your requirements, you are out of the game. So usually you put more power than what is required. But if you put less, then obviously you need to go back to the drawing board. So the frequency selective. So this part we are focusing on frequency selective predefined filter, and this will help us to understand the. Let's say I have a complex frequency. Why we choose an exponential j omega naught n? We will shortly see that any digital signal can be broken into some of these frequencies. So a signal is nothing but a lot of exponential j's, j omega naught n. Omega naught n is a frequency, because I know this is an Euler identity. It is in fact cosine of omega naught n plus j. And you deal with complex signals a lot in signal processing. Okay, in analog system, the concept of imaginary is imaginary. You say imaginary is something which is not real, so you cannot really have an imaginary thing in your system. But interestingly, in signal processing and digital communication, very first thing you do is usually you make it imaginary. You make it complex. So because this is just a software, in software you know how to handle complex numbers. They're very effective. So that is the reason that you, instead of just saying what will happen